Ahí está.
Okay, so ready? Okay. Hello everyone. How are you? This is our presentation about our version of the design, construction, and modeling of our water power rocket. First of all, we would like to meet our astronauts. First of all, your server, Ivana Montenegro. Pasco.
Me, Paula Costa Torres.
Gerardo López.
Héctor González,
Andrés Antonio González.
and we are team number 5.
So the challenge was to construct a propelled rocket. We did it in these 5 weeks, and our objective was to reach at least 80 yards. And considering the Bernoulli's principle and some other types of the motion, especially parabolic motion, and other forces that are influenced, like gravity. The purpose was to reach at least 80 yards by designing a mathematical model and also physical that describes the launching of the rocket.
Now, for the construction of the rocket, first we cut the two bottles to the required measurement. Then one will be the base and the other will be the top. Then we insert the middle section of the other bottle in the bottom to reinforce the structure. Then we add a cap of another section of the close of the top of the securely, and then we use tape to connect all and secure the parts. And with that, we will have the body of the rocket that it's shown.
And for our air inlet system, we use a half-inch PVC tube, and in one end we use epoxy clay in order to make a seal. And here is like the air entrance. And in here, in the other end, we use insulating tape in order to fill the width of the water bottle, so the pressure and the water does not come out of the bottle. So what are some areas of opportunity of our design? First of all, valve with measurement of the pressure will be very useful in order to make the calculations, and also to prevent something that happened to us is that the rocket exploded, because we don't have a way to calculate really how much pressure it stands before it explodes. Then a better seal mechanism to prevent explosions would be useful, because although the seal is very efficient, it is so efficient that it maintains the pressure inside the rocket at the point that it can explode. So it would be better to use a better sealing mechanism that at the limit the pressure the rocket can withstand, it basically starts exerting pressure. Then is better application of the weight at the tip, because we had a lot of problems first of all with the weight of the tip. It had a lot of weight, so the rocket tended to go down. The parabolic motion was very aggressive, so we put less weight. And then a better planning for the designing of the base. Although this base worked well, the first idea was to use a cardboard base that basically failed because it got wet and it broke.
Now, some other things of the rocket is that the weight on the top, we put a weight that will help the rocket to maintain its trajectory and have a greater air resistance. The spoilers are proportional to the size of the rocket to help with the stability, aerodynamics, and direction of the rocket. And for the amount of water, we use the 40% of the capacity of the bottle to fill it with water to the.
So we have like the sketch of the rocket design. So here we use the measurement for the whole system. We have a tip at 7 centimeters, and what Hector said was like the spoilers or the like the wings of the system. We use the wings proportionally to the size of the rocket and made measurements, and we came along that 30 degrees was the optimal angle for the wings, and we use trigonometry to efficiently calculate like the length and the width of the wind.
So here's a quick video of the first test of the rocket, which was very successful. It reached, if I don't remember what
87.
that is,
87.
87 yards, which was actually very surprising. And I'm going to explain very generally the laws and principles that are used in the whole experiment. First of all, is the conservation of linear movement, which help us to understand the force that is exerted thanks to the water in the rocket. The Bernoulli's principle is going to help us understand the relationship between the pressure and the water that comes out of the rocket. Newton's laws of motion are going to help us to first understand a very important principle, which is inertia, which is one of the principles that work on the rocket, since it relies on inertia to complete its movements, and also force, which is mass times acceleration. We have continuity equation, which is gonna help us to understand what happens when the mass conserves between a larger area or a shorter area when the water comes out. And finally, the most important to get the result, the parabolic cinematic movement, which is going to help us to optimize the movement of the rocket, the distance it reaches, and basically this one integrates all of this.
Now the calculus for the previous slide. First, we're going to start with conservation of linear momentum. This pushes the water. This explains that when the water flows out in a vertical movement, the conservation of linear momentum is the speed of velocity and is related to the loss of water and mass to the change of velocity. Here we have the formulas and the example picture. Now the Bernoulli equation is used to determine the velocity that is derived from the pressure difference inside the rocket and the external environment. Here the P is the pressure difference, the density of the water, and the height difference. Now the Newton's law of motions. First we have the second law that describes how the rockets react to velocity changes and it loses mass due to the exposure of water. Here we have with masses and the continuity equation that connects the behavior and change in the fluid's velocity section areas and the deposit inside the rocket. Now we have the parabolic motion that is the Newton's second law. And it's applied on the external forces acting on the rocket. Here is the gravity, and we have the air resistance acting against the rocket's motion. Finally, we have the parabolic, the parabolic cinematic of motions, and it's divided into position equations and velocity components for the x and y and for the x and y. It is used to describe motion when it flows a parabolic trajectory under the influence of gravity.
So this is our table for the results under the tests we did last week. Yeah. So throughout these tests, we use different equation angles and different volumes, and that's why, like Hector mentioned, 40% volume was our optimal volume, and we found the equation at 45 degrees, which we made 87 yards.
And that would basically be the end of the presentation. Thank you for your attention.